solution and colligative properties. So the first thing we're going to look at is the properties of aqueous solutions, and we're going to look at solubility rules, which are basic rules that govern which kinds of compounds are going to be soluble in water or not. And that will be what we're going to do today. I'm going to try something tomorrow, which is I want to try using Kahoot to give you a quiz. Have you had any of your teachers do that yet? Try that? I don't know if it's going to work or not, but. So we'll see how that works. Anyway, so what I'm going to do today is describe something called dissociation, what happens to ionic compounds when you put them in water. And then we're going to go over the solubility rules, and we're going to practice predicting whether or not a compound will be soluble based on those rules. Okay, so first thing is dissociation. Now, I don't know if I mentioned before, does somebody have a microphone on? Because it's something I hear glitchy. Just make sure your microphone is muted. So there's a difference between dissociation and something called ionization. Dissociation is when you have an ionic compound like sodium chloride and you dissolve it in water, and you are literally just having the ions which already exist separate. Okay, so there are ions present in sodium chloride solid. It's just in solid form. But as soon as you put it in the highly polar liquid water, the polarity of the water is strong enough to actually pull the ions apart. That's called dissociation. So dissociation in general as an English term just means like you stop being connected. It's the opposite of association. If you are associated with something, it means that you're connected to that thing. If you dissociate, that means that you stop being connected. Ionization is a completely different process. I don't know if I've talked about this before, but I want to make sure that I emphasize this point. Ionization is where you have a substance which is not ionic. So hydrogen chloride gas is a molecular compound. When you dissolve it in water, because hydrogen chloride is a very highly polar compound, the water and the polarity of water is actually able to create ions. So you end up with a hydrogen ion, which of course will become hydronium, and chloride. So ionization is the process of actually creating ions from something where ions didn't exist before, but dissociation is just taking ions and separating them. So I just want to make sure that we understand the distinction between those two. So an ionic compound dissolves in water, the ions separate. So the dissociation is just the separation of ions that occur when an ionic compound dissolves in water. Like here we have, excuse me, I'm so sorry. I'm apparently boring myself. When sodium chloride dissolves in water, again, the sodium ion and the chloride ion exist already as a solid, but they just separate. And another example is calcium chloride. It will form calcium ions and chloride ions. Again, it's dissociation, not ionization. The first thing that we want to look at is the number of ions that are not, I almost used the very wrong word. The ions that are separated compared to the formula unit in a balanced equation. What I mean is, if you have 1 mole, for example, 1 mole of calcium chloride, and you dissolve that in water, you're going to separate 1 mole of calcium ions and 2 moles of chloride ions. So if you have 1 mole of solid calcium chloride, you'll create 3 moles of ions. Sorry, I used the wrong word, not create, you will separate. They will separate into 3 moles of ions. Okay, for sodium chloride, you have 1 mole of a solid, which will separate into 2 moles of ions. This is going to be extremely important when we talk about colligative properties, I believe in section 3. Get the book out. So section 1 today is mostly just about solutions, and especially solubility rules is the really important part. I'll talk a little bit about net ionic equations a bit later. And then we talk about, colligative properties in section, it's so dark, I can't see it, section 2, looks like. Anyway, so this concept is going to be very important, and I'll bring it back next week when I talk about colligative properties. So for ionic compounds, when you dissolve them in water, it's going to form or be separated into multiple moles of ions. So 1 formula unit of sodium chloride gives 2 units of ions in solution, and for calcium chloride, it's 1 versus 3. For this idea, we assume 100% dissociation, that meaning that all of the sodium chloride molecules separate into ions. For soluble ionic compounds, you can always assume 100% dissociation. Okay, so what if I ask you to write the equation for the dissolution, is another word for dissociation? Well, I mean, not really, but they're related. So dissolution is just the process of dissolving, which results in dissociation. So dissolution leads to dissociation. All right, so we have aluminum sulfate in water. So can anybody remember how to write chemical formulas? That's probably worth reviewing. Does anybody remember what the formula for sulfate is? Yeah, and the charge?
-3.
Close.
2 minus
-2, yeah. And aluminium is in group 13, and it's a metal, so it's +3. So if you're being super lazy about it, you just move the 3 to sulfate, the 2 to aluminum, so we get Al2SO4 3. Don't forget your brackets, because when you want to have multiple numbers of polyatomic ions, you need the brackets to show I want 3 of SO4 altogether. All right, so when that separates, you're going to get aluminium, which is +3, aqueous. Now this is going to be the one chapter where the state is going to matter. So if it's dissolution, we're starting with a solid, and our ions, of course, are aqueous. And then we balance the equation by putting a 2 there and a 3 there. So if we have 1 mole of aluminum sulfate, we're actually going to form 5 moles of ions, 2 of aluminum, 3 of sulfate. Okay, going through the same thing basically. Okay, so I'm just going to go through these quickly, mostly to kind of review writing formulas and stuff, but also just to practice this. So first thing we're going to do is ammonium chloride. Anybody remember the formula for ammonium? It's one of your polyatomic ions. NH 4 and charge?
+1.
Correct.
+1.
Yep. All right, so then you just put those together, NH4Cl. And again, solid, you'll form NH4 plus and Cl minus. So if you have 1 mole of ammonium chloride, how many moles of ions will that give you? So total number of moles of ions after dissociation. How many moles of ammonium are there? If there's no coefficient in front, what number does that indicate?
1.
Okay, and chloride?
1.
1. So 1 plus 1 is
2.
2, yeah. So 1 mole of ammonium chloride produces 2 moles of ions. Okay, sodium sulfide. What is the formula for sodium sulfide?
And
Is it
Na2S.
Yes, it is.
Na2.
Yep. Sodium is +1. Sulfide comes from sulfur, which is -2. So Na2S, Na plus S minus 2. Balance the equation. How many moles total do we have here?
3.
3, exactly. And finally, barium nitrate. Any ideas on formula?
BaO3.
NO3.
No.
2.
second?
Yeah, barium's +2, nitrate is only -1. So BaNO3, 2. You have Ba, 2NO3. All right, now here's the thing. Now we're starting with half a mole. How many total number of moles do we have after dissociation?
1.5.
Yeah. Yeah, because if you look at this as a 1-to-1 ratio between BaNO3 and Ba, so if BaNO3 is 0.5, Ba is 0.5. The mole ratio between barium nitrate and nitrate is 1-to-2, so this is 1 mole for a total of 1.5. Correct. All right. Now, sometimes when you mix 2 liquids together, and I'm really sad that we're not in school because this is one of the most fun experiments to do, where you almost literally just get to like mix a bunch of crap together and try to like make a precipitation reaction happen. Depending on when we get to go back, maybe we can come back and do some of these experiments and of course, write a lab report with that. Okay, so sometimes when you mix 2 solutions together, an insoluble solid is formed. So even though, let's say in the previous examples, we had sodium chloride and barium nitrate. When we mix those together, and here's why it's important to understand if I write AQ, what that actually means. If I write AQ, it's important to get that this indicates that you're really talking about these ions in a solution. You're not talking about NaCl anymore. You're talking about sodium ions and chloride ions in a solution. Same with barium and nitrate. So if I were to take these 2 solutions and mix them together, I would have to look at, is there any combination of these 4 ions that creates a compound that is insoluble in water? So obviously it's not going to be sodium with chloride and it's not going to be barium with nitrate because those are already soluble in water as seen by the initial solutions. Weird sound from my dog. So what I would have to do is then say, okay, well, obviously barium and sodium are not going to combine because they're both positive ions. The nitrate and the chloride aren't going to combine. So what possible combinations could I have? I could have barium with chlorine or chloride, and I could have sodium with nitrate. So my possible products are NaNO3. I don't know why my N's are so weird today. NaNO3 and BaCl2. So then my job would be to try to figure out if either of these compounds is insoluble in water. And lucky for you, there is a set of rules that you can follow. And from what I understand, yes, you're going to have to remember these rules. So let's just go through these one by one. Some of them are going to kind of be repeats, and so you can pick and choose how much of it you have to remember. Number 1 and number 2 are the most important ones, because you'll find a lot of compounds contain these ions. So number 1 is sodium, potassium, and ammonium compounds are soluble in water. It does not matter what anion these ions are paired with. If your compound has either or any of these 3 cations, it's going to be soluble in water. And number 2 addresses 3 anions, which make a compound soluble in water. That's nitrates, acetates, and chlorates. So if I go back to my previous example, my first possible combination of sodium nitrate, you can apply rule number 1 and rule number 2 to this compound because it has sodium, which makes it soluble, and it has nitrate, which makes it soluble. So absolutely, that's not going to precipitate because it is soluble in water. It's going to stay as ions. Okay, moving on to number 3. Most chlorides are soluble except those of silver, mercury, and lead. And then it goes on to say lead 2 chloride is soluble in hot water. Okay, well, I can't really think of an example of a question that would be so tricky as to have you remember one particular version of lead chloride and give it to you in hot water and then expect you to remember that's soluble. Oh, sorry, insoluble. Oh, sorry, soluble in hot water. Yes. Blech. So for chlorides being soluble, chlorides are soluble except silver, mercury, lead. So of course we go back to the previous example. Barium is not one of those 3. So barium chloride will also be soluble in water. So the bottom line here is if you mix sodium chloride and barium nitrate together, nothing will happen. I know, like serious letdown, but that's just what I mean by predicting precipitates. If you take 2 solutions, you mix them together, look at your possible combinations of ions, apply your solubility rules, and then decide, is either one of these products insoluble in water? If it's not, you would say, if I asked you if it was a reaction, you would just write NR, no reaction, because nothing's going to change. All right, moving on to sulfates. Most sulfates are soluble except barium, strontium, lead, calcium, mercury. So first, looking at barium, strontium, calcium, these are all group 2 metals. So it's a pretty safe assumption that if you combine a group 2 metal with sulfate, it's insoluble. And notice that we also have lead and mercury again. Okay. So another thing you could do is say, okay, if it's lead and mercury, it's insoluble unless it's with these 3. So then you would only really have to remember, again, rule number 2, that nitrates, acetates, chlorates, all soluble. Carbonates, phosphates, silicates, insoluble. And I know that it says except those of sodium, potassium, and ammonium, but you don't even have to remember that because that would be when rule number 1 would apply. So all you have to do is remember carbonates, phosphates, silicates, insoluble. But if you've got sodium, potassium, ammonium, it's soluble. And the last one, most sulfides are insoluble except those of calcium, strontium, and then again, rule number 1. And pointing out again the calcium and strontium. So group 2 and sulfides, soluble, and rule number 1. So let's practice. Is calcium phosphate soluble or insoluble? So you have to go to the rule on phosphates, which is rule number 5, which says most carbonates, phosphates, and silicates are insoluble except those of sodium, potassium, ammonium. So calcium is not one of those 3. So calcium phosphate is insoluble. I hope that makes sense. If it does not, please make sure you speak up or put in a chat or something so that I can explain better. So if something is insoluble, of course, we don't write dissociation equations for them because there's literally no products. The biggest thing that we use the solubility guidelines for is predicting if a precipitate will form if you mix 2 solutions. If that mixing results in a combination of ions that form an insoluble compound, a double replacement reaction will occur. If you remember from last year, double replacement was one of the 5 types of chemical equations we looked at. We had single replacement, double replacement, synthesis, decomposition, and combustion. Double replacement was when you just swapped ions, if you don't remember that. Okay, will a precipitate form when solutions of ammonium sulfide and cadmium nitrate are combined? So first thing you want to do is write your formulas. Formulas are really important. So this is going to be a really good review lesson of chapter 7 when we wrote formulas for compounds. So ammonium is NH4 plus. Sulfide comes from sulfur, which is -2, which makes ammonium sulfide, NH4. Oops, I turned white all of a sudden. 4,2S. And that's aqueous because it's solutions. Again, I did say that this time we have to pay attention to the state, because when I ask you to write these equations, state is going to count very, very much. And then we have cadmium nitrate. Cadmium is +2, nitrate -1. So that's CdNO3 2, again, aqueous. So your 4 ions that are possible to mix and match, we have ammonium with nitrate, and both ammonium from rule number 1 and nitrate from rule number 2 are soluble. So ammonium nitrate is also going to be aqueous. So that is not a possibility. The other possible compound is cadmium sulfide. So then you have to go to rule number 6. Most sulfides are insoluble except those of calcium, strontium, and then rule number 1, sodium, potassium, ammonium. Cadmium is not one of those exceptions, so this will be an insoluble solid. You will be able to write a full equation for that. So you get NH4NO3AQ plus CDS solid. And this is why state is important, because in this way you are indicating that a precipitate forms. Okay, So I went through all that already. Okay, so we've got the two possible products, ammonium nitrate, which is more than soluble because ammonium compounds are soluble and nitrate compounds are soluble. Calcium sulfide, of course, goes to rule number 6, which I just read. So this is what it looks like. And this is what I wish we could do in the lab, because what I would do is normally tell you, like, of all of the chemicals we have in the cabinet, go ahead and make small solutions of different combinations and mix them together, predict what you think will be able to form precipitate, and then try it out. And it's, like I said, it's like some of the most fun that we ever have in lab, but the world has to suck. So last thing, do I have time? Yeah, okay. The last thing is net ionic equations. Now, I'm just going to summarize this instead of going through the whole blah, blah, blah. The way that this works is, let's go back to the previous example. So we've got, all right, putting my hand down just makes sense. What did we have? Crap, I completely forgot. All right, cadmium nitrate, ammonium sulfide. All right, ammonium sulfide, cadmium nitrate. All right. Okay, so here's what we start with. Now, there's going to be two ways to write these equations. The first one, which I don't think I'm ever going to have you do this because it's just a complete waste of time, in my opinion. And it doesn't really serve a purpose, but there's something called an overall ionic equation. And that is when you write out all of the ions separated. For anything that can be separated, you separate them. So let's just write the overall chemical equation, which we did, which was then NH4NO3 AQ, I'm going to run out of room, plus CDS solid. And then we balance. So NH4NO3 becomes a 2, and that takes care of that. Okay. So this is the chemical equation. Now, if I were to write that in an overall ionic equation, here's what it would look like. You would have to take all of the aqueous things and separate out every single ion and have it balanced. So you would have to write 2 NH4 plus AQ plus S minus 2 AQ plus CD plus 2 AQ plus 2 NO3 AQ yields 2 NH4 plus AQ plus 2 NO3 minus AQ plus CDS solid. Oops, like you get it anyway. Boy, no, go away. All right, so this is what is called the overall ionic equation. I suppose it has a little bit of use insofar as that when we start balancing redox reactions later, you have to learn how to separate ions out, but I don't think this is a necessary step to take. As long as you understand that if something is aqueous, it means that technically in the solution, they're present in ion form and not as a formula unit like this. But it is good for me to write out the overall ionic equation for you in order to explain to you what the net ionic equation is. So, excuse me, if we look at the left-hand side versus the right-hand side, you will notice that there are two ions that are present as ions on both sides. So in essence, they have not changed. Nothing has happened to them. That is sodium and, ammonium and nitrate. They are ions as reactants and they are ions as products. They have literally done nothing as far as the reaction is concerned. We call these spectator ions. And there's a reason why we use the name spectator, because they literally just, well, not literally because they don't have eyeballs, but they just watch the reaction occur. They don't actually take part in the reaction. So when we write our net ionic equation, we are going to remove the spectator ions because they do not participate in the reaction. So our net ionic equation would just be the sulfide ion, the cadmium ion, and then the precipitate. That's it. It would not include the spectator ions. So there's a difference between the overall ionic equation where you see everything, including the spectator ions, and then taking out the spectator ions, you write the net ionic equation. Okay, that's all I'm going to do